Hi, my name is Guillermo Santamaria Bonfil, and the work I'm presenting is named Knowledge Modeling for Ill-Defined Domains Using Learning Analytics, Lineworkers case. E-learning and most intelligent tutoring systems, in short ITS, have been devised to provide any given individual more or less personalized support for learning about a given knowledge domain. Delve ITS have ranged from classical expert systems to machine learning algorithms and hybrid models, all with different levels of success in real applications. The main component of any ITS is knowledge per se, thus we need a model for it. Such model needs to consider the knowledge nature, for instance if it is well defined, such as the area of Boolean logic. Also, how is knowledge constructed, and how can we validate it and evaluate it? To address these questions, the epistemological analysis and the computational implementation are carried out. The former decomposes a knowledge area into the domain model, which corresponds to facts and declarative knowledge, for instance, concepts, properties, relationships, and so on, and the problems model, where the inference machine is established. This is the processes to solve a problem. On the other hand, the selection of the computational implementation is consequence of the epistemological analysis. Some formal tools are ontologies, predicate logic, semantic networks, and so on. ITS are effective in well-defined knowledge domains, where general-purpose languages such as first-order logic or other systematic methods can be used to build facts and validate solutions. Unfortunately, there are many human knowledge domains that are ill-defined. This is, they lack of a strong theory uniquely specifying on one part the concepts, procedures, and their relationships, and on the other how to validate solutions through a formal procedure. These have a large and complex solution spaces that prohibits identifying all possible solutions. Hence, the verification heavily depends on human experts. Consider, for instance, the case of arithmetic. We can define within the domain the key principles underlying addition and subtraction as rules that are formally validated. On the other side, the validation for carrying out properly a maintenance procedure is not straightforward. One area which can be considered ill-defined is the technical and vocational education and training, in short TVT. Programs developed around job requirements defined by the industrial sectors. TVT is composed of both theoretical content for a specific job and tacit experience obtained from an apprenticeship. Further, TVT is a competency-based education which focuses on program goals and work objectives. Competencies are organized around predefined abilities or skills that are the outcomes of the curriculum. A particular job case of TVT is Lineworkers. These are the staff required by a public or private utility for maintaining and repairing its electrical transmission and distribution infrastructure. Lineworkers education involves physical preparation, knowledge on physics and electromagnetism, theoretical and tacit knowledge regarding maintenance maneuvers execution, as well as hygiene and safety industrial rules. Information regarding competencies, theoretical knowledge, and best practices is stored within text documents, either as a standard competency definition, an operational manual, or a traditional textbook. To pour this knowledge into an ITS, we first require to recharacterize it. This process consists in obtaining the relevant concepts and relations within a domain through the eyes of several human experts. Yet, defining the model building blocks in this way is expensive, slow, and error-prone. Thus, to build a knowledge model from text sources, first we need to define the concept model. In this sense, by model, we refer to a concept map built upon concepts organized hierarchically, using a semantic distance measure inspired in the Kolmogorov complexity, namely the normalized web distance. The proposed knowledge model has a layered top-down organization, from competencies on the top to the domain model on the bottom. For building such model, the next process is followed. First, a text mining preprocessing step is carried out to standardize text, remove stop words, and extract concepts. It is worth to mention that, depending on the technicality of each knowledge domain, units and special acronyms may not be removed during the text preprocessing due to its importance. Then, a hierarchical clustering is used to construct a concept map for each layer using the normalized web distance. Nevertheless, we may have situations in which we need to determine what have in common an insulated wire tongue, and a hammer. While some concepts or expressions have a literal meaning, such as remove the plastic insulator, others have non-literal interpretation. Thus, they do not contain information within themselves, and require context and human knowledge to acquire their meaning. For instance, the word hammer. The sequence of letters or the word itself does not provide any information regarding what a hammer stands for or how it is used. Yet, we can compare the semantic similarity of non-literal objects through the normalized web distance. Using a web search engine or any large text corpus, this metric infers a semantic relationship between concepts from the number of hits returned by the search engine for a given set of keywords. Keywords with the same or similar meaning or that appear in the same context tend to have a normalized web distance value near zero, while words with dissimilar meanings and context tend to be equal to 1, or even infinity if objects do not appear together on the same document but do occur separately. So, for this case, the normalized web distance is 0.63, meaning that both the insulated wire tongue and the hammer are related, since both are tools, but they are used in different contexts too. On the other side, a more specific spare part for carrying out power lines maintenance, such as a pin insulator, attains a 0.19 value with the insulated wire tongue, due to a closer relationship within the context of power grid maintenance and insulation. Now we present the results for building a knowledge model. In this work we focused on the text documents used by an e-learning system for the training of line workers in maintenance maneuvers carried out over the power infrastructure. Since we are only focusing on tools, we are building the lowest layer, the domain model. Tool names are in Spanish. The hierarchical clustering is built using the complete linkage criteria. We employed 5 clusters, although the number of clusters is not determined optimally. To measure the normalized web distance, we employed 2 search engines, namely Bing from Microsoft and Google from the same company. To improve discussion, we only show results for the 31st tools, sorted alphabetically, and kept the normalized web distance to 3 instead of infinity. Here is shown the resulting model using the Google search engine. Observe that, for 5 clusters, all of these tools can be considered similar. This is the normalized web distance is below to 1. However, when we reduce the number of clusters from 5 to 3, due to the complete linkage criterion, we found that the resulting clusters are totally dissimilar. This is the normalized web distance is above 1. In this sense, there are documents where pairs of tools appear together, but there are others with no relation at all. To compare the similarities and differences between 2 domain models, we employ a tanglegram. This is a plot to visually compare 2 hierarchical clusterings by placing them horizontally, facing each other by the leaves. Items in leaves are matched by connectors. Branches that contain a unique subset of items are highlighted with dashed lines, and common subtrees in both hierarchies are presented in solid lines. The quality of the hierarchy's alignment can be measured by a function called entanglement. It measures the alignment by penalizing crossings of connectors using a L-norm function. It ranges between 1, full entanglement, and 0, no entanglement. A lower coefficient value corresponds to a better alignment between concepts and clusters, although this does not guarantee that the trees are equivalent. For convenience, we replace tool names for IDs in the tanglegram. Observe that in our case, at leaves level, several subtrees are conserved in both hierarchies. In contrast, items combination at the level of clusters are depicted by dashed lines, pointing out that most combination of elements are not present in the other tree. This disagreement between the Bing and the Google hierarchies is corroborated by the entanglement function using a L1 norm, resulting in a 0.43 of entanglement. In this work, we built a knowledge model from text documents based on learning analytics for the ill-defined domain of line workers education. However, the proposed approach can be applied to any educational setting where text documents are available. Concepts within the same cluster may be considered part of the same topic. Thus, an ITS may exploit this by presenting similar objects to a student during a training session. Still, we need to answer what does the hierarchical relations stand for and how can we bring into consensus hierarchies obtained from different corpus. Thank you.